A colossal stone platform can stand for thousands of years without a single steel beam. The secret to this endurance is a lost art of engineering, a puzzle we are only now beginning to solve. By the end of this, you will understand the universal principles that allowed ancient builders to defy gravity and time. We will uncover how they chose unshakable ground, mastered materials, and even planned for the slow settling of the earth itself. How did they achieve such perfection without modern tools? Their methods reveal a profound dialogue between human ambition and the natural world. What do you think it means for a structure to be built for eternity? The decision to build something that would outlive generations began with a question that echoes across time. A community gathers not with blueprints, but with a shared vision. They need a place to stand together, to reach toward something greater than themselves. This was not about mere shelter. It was about creating a stage for the stories that defined them, a permanent anchor point in a changing world. This fundamental human need for a sacred, elevated space presented the very first engineering puzzle. How do you give physical form to a spiritual idea? How do you make a promise in stone? Experts studying the earliest sites, like the astonishingly ancient Göbekli Tepe, see this impulse carved into the landscape itself. The platform was not just a construction project, it was an act of belief. It declared, "We are here and this place matters forever." This desire for permanence drove every technical decision that followed. Before a single stone was moved, the most critical choice was already made: the selection of the earth itself. The first and most brilliant stabilization technique was to build where the earth was already stable. Ancient builders possessed a deep, intuitive geology. They sought out the bones of the landscape, the unyielding bedrock or stable, compacted geological formations that would not shift or settle unevenly. The location was never accidental. A site chosen for ceremony or gathering was also chosen for its inherent strength. Consider the platform at Stonehenge. It was built upon a natural bed of chalk, a substrate that provided not only a firm foundation but also crucial drainage, preventing water from pooling and softening the ground beneath those immense stones. The earth itself became the first member of the building team. This tells us something profound. For these builders, the practical and the symbolic were woven together. The permanence of the bedrock mirrored their desire for a permanent legacy. They were not conquering the landscape, but partnering with it, finding the places where the earth was willing to hold their ambitions aloft. What does this ancient search for a firm foundation tell us about our own world? What structures do we build today that symbolize our deepest hopes for something lasting? To answer that, we must look closer at how they prepared this sacred ground. The ground was chosen, but the work had only just begun. Before the first cornerstone was laid, the ancient engineer had to listen to the earth. This was not a science of instruments, but of intuition, of reading the landscape like a living text. They understood that the greatest enemy of a massive platform was not time, but the ground it stood upon. Unstable, waterlogged soils could silently shift, causing catastrophic settlement. Seismic zones posed a threat of sudden, violent movement, so they learned to see what we might miss. They avoided floodplains and loose, sandy deposits, seeking instead the unyielding promise of bedrock outcrops or dense, compacted clay bases that would hold firm for centuries. At Tiwanaku in Bolivia, the builders did not just place their monumental platforms anywhere. Geoarchaeology reveals they meticulously aligned their structures with stable geological strata, using the natural lay of the land as a blueprint. They sought out natural terraces and ridges, which dramatically reduced the amount of earth they needed to move, letting the existing topography do much of the work. How did they know where to build? They read the clues left by nature itself. They dug test pits to feel the soil's consistency, observing how different layers compacted. They studied natural erosion patterns on hillsides, seeing which soils held fast and which washed away. This geological acumen was their first and most powerful stabilization technique. Sometimes the perfect symbolic site was not on perfectly stable ground. This is where human ingenuity truly shines. Consider the Olmec platforms at La Venta, constructed in a swampy region. The builders did not abandon their vision, they adapted it. They created colossal artificial mounds of packed earth and clay, constructing their own stable islands in the unstable wetland. They were not just building on the land, they were building the land itself. This ancient, intimate dialogue with geology stands in quiet contrast to our modern world. Today, we often choose a site for convenience or economics, then use technology to force the ground to comply. We pour deep concrete pilings and complex drainage systems to correct for poor choices. The ancient approach was one of harmony, of finding where the earth was already willing to bear the load. It asks us a subtle question. In our rush to build, have we forgotten how to listen to the foundation of everything? Once this sacred, stable site was confirmed, the next challenge awaited, transforming raw, unpredictable stone into a perfect, interlocking puzzle. The chosen earth was only the beginning, for a stable foundation demands perfect balance. A platform built on a slope, no matter how solid the ground, would create a silent, relentless pressure, a slow-motion slide into ruin. The ancient builder's second principle was the art of creating a level base, a uniform surface where every stone would bear its share of the weight equally. Without laser levels or digital transits, they achieved this with an elegance born of necessity. Their tools were humble, yet their thinking was profoundly sophisticated. They used the most reliable level known to humanity, water itself. By digging shallow trenches and filling them with water, they created a natural horizontal plane. A mark made on a stake at the water's surface at one end of the trench could be transferred perfectly level to the other end, establishing a true datum point across the entire site. Simple wooden frames with a plumb line or long sighting rods aligned by eye extended this level line over great distances. At Machu Picchu, the precision is breathtaking. Engineering historians studying the site note the platforms supporting the temples are so perfectly level that the implied mathematics, the understanding of plane geometry, is extraordinary. They achieved this through a masterful technique called cut and fill. Instead of trying to flatten a whole mountainside, they carved terraces directly into the bedrock, cutting into the slope to create a level shelf and using the excavated stone and earth to fill in the lower areas. This created a series of stable, reinforced ledges, each one a perfectly level stage for construction. But a perfectly flat surface could trap water, and water is the silent destroyer of foundations. So sometimes a slight, intentional incline was engineered into the base, a gradient so subtle it is invisible to the eye but enough to guide rainwater away, protecting the integrity of the earth below. The Ziggurat of in ancient Mesopotamia showcases this layered approach. Its core is a mountain of baked bricks, but beneath that, the builders laid a carefully engineered foundation of compacted gravel and sand. This layer served a dual purpose. It provided a level bed, and its porous nature acted as a drainage plane, pulling moisture down and away from the heavier structure above. Picture the effort, the communal focus required to level a vast area using only strings, water, and human sight. It was a patient, iterative process of checking and rechecking, a physical dialogue between the builder's intent and the reality of the land. This meticulous creation of a level base was an act of profound foresight, ensuring the immense weight to come would be distributed not as a burden, but as a shared responsibility across the entire foundation. And upon this carefully prepared stage, the next act of the drama would unfold, the selection and shaping of the stones themselves. The level base was prepared, a perfect canvas awaiting its first stroke. But for the most ambitious builders, simply placing stones upon the ground was not enough. They sought a deeper union, a bond so permanent it would make the structure and the earth one single entity. This is the principle of direct integration, where the platform does not sit on the bedrock, it grows from it. Visualize the first massive foundation stones, not as separate blocks hauled into place, but as extensions of the living rock itself, carved and shaped in situ. This technique eliminated the weakest link in any construction, the interface between the man-made and the natural. By cutting trenches and sockets directly into the bedrock, then fitting the first course of stones into these negative spaces, they created a mechanical lock. The platform could not slide or settle independently because it was physically keyed into the unshakable foundation below. Stonemasonry traditions from around the world speak of this practice. It required immense effort upfront, quarrying and shaping the stone right at the building site to minimize stress and ensure a perfect fit. The process was one of revelation, not just construction, as if the builders were uncovering a form already sleeping within the mountain. A stunning example is the platform of the Temple of the Sun at Meroe. Here, the architects did not build a temple and then place it on a hill. They instead approached a natural sandstone outcrop and began to carve. The rear walls and the sacred inner chamber were sculpted directly from the bedrock, while the front colonnade and platform were built out from it with precisely fitted masonry. The result was a monolithic structure, half born of the earth, half raised by human hands, each supporting the other in an eternal embrace. To further secure this bond, builders employed stone pins and dowels. These were not mere pegs, but carefully shaped stone tenons fitted into matching holes drilled into both the bedrock and the foundation stone above. Once seated, these hidden connectors locked the two layers together, resisting any lateral force from wind or tremor. This method transformed the platform from an object placed upon the landscape into an integral feature of the landscape itself. It represents the ultimate expression of stability through unity. But this leads us to a compelling question. What happened when the vision called for a platform in a location where the bedrock was too deep or simply not present? When the earth refused to offer its solid bones, how did human ingenuity respond? The answer lies in one of history's most ingenious and patient inventions, a foundation that could be taught to carry the weight of mountains. When the bedrock was too deep or the soil too soft, ancient engineers did not retreat. They built a new earth from the ground up. Their solution was a layered defense, a masterpiece of artificial geology constructed with profound patience. This was not simply dumping fill, it was a deliberate, stratified engineering of the ground itself. Picture the process, a communal rhythm of labor repeated for generations. First, a layer of large, jagged stones was placed, creating a porous drainage bed. Upon this, a layer of smaller gravel was spread and compacted. Then came alternating strata of clay for impermeability, sand for stability, and sometimes even woven reed mats or organic material to add flexibility and bind the layers together. Each stratum had a specific purpose, working in concert to create a foundation that was greater than the sum of its parts. The key insight was understanding compression. The builders knew the immense weight of the final platform would slowly press these layers down, squeezing out air and moisture, locking them into an ever denser, more stable mass. They were not just building a platform, they were teaching the earth beneath it how to bear a monumental load. The alternating coarse and fine layers acted like a natural filtration and stabilization system. Water from rain or groundwater could seep down through the gravel, but the clay layers would prevent it from rising back up into the structure, protecting the core from the destructive cycle of freezing and thawing, or from becoming waterlogged and weak. A brilliant example of this practice is found far from the arid deserts, beneath the palace of Knossos on Crete. Archaeological excavations reveal a complex, engineered substrate beneath its massive central court. The Minoan builders did not trust the native soil alone. They excavated deep trenches and filled them with a carefully sequenced sandwich of materials, including crushed limestone, clay, and even ceramic fragments, creating a rigid, well-drained raft that has supported the palace for millennia. This method required a deep, almost intuitive grasp of material science. How did they know which stones to use, which clays would bind best? Their laboratory was the landscape itself. They learned by observing how different materials behaved in their natural environment. A riverbank showed them how rounded gravel allowed water to flow, while a clay bed held a pond. They sourced materials not for convenience but for specific engineering properties, selecting stones for their crushing strength or clay for its plasticity. This layered approach represents a shift from finding stability to manufacturing it. It speaks to a growing confidence, a belief that human knowledge could engineer permanence even on reluctant ground. It turns a potential weakness into an engineered strength, creating a foundation that actually improves under the immense pressure it was designed to hold. This clever use of layered, compacted earth leads us to the very heart of the material they were striving to support, the stones themselves, and the hidden genius of how they were chosen and shaped. The layered earth was ready, but its true purpose was to receive the heart of the platform itself. The stones chosen for this task were not merely convenient, they were the result of a deep geological wisdom. In the quarry far from the building site, the most critical stabilization decision was already being made. Builders understood that not all stone is created equal. For the massive foundational courses, the hidden layers that would bear the unimaginable weight, they sought out the most unyielding materials the earth could offer. They passed over softer, more easily worked sedimentary stones like limestone or sandstone for these critical roles, knowing these could crumble or wear away over centuries. Instead, they journeyed to distant sources for igneous and metamorphic rock, for granite, basalt, and andesite. These stones, born from volcanic fire or immense subterranean pressure, possessed a crystalline structure that gave them extraordinary compressive strength. They could resist the crushing burden of the platform above and endure the relentless assault of wind, rain, and freezing temperatures for millennia. This was a choice that considered time on a scale we rarely contemplate today. It was an investment in permanence, where the difficulty of quarrying and transporting such dense material was outweighed by a singular goal, that the foundation would never be the point of failure. Petrology, the study of rocks, reveals the intentionality behind these choices. At Teotihuacan, the builders did not use the local, softer volcanic tuff for the core of their massive platforms. They went to great effort to quarry andesite blocks, a much tougher volcanic stone, for the foundational layers. This stone's density and resistance to weathering made it the perfect hidden skeleton upon which the city's plastered facades could shine for ages. But selecting the right stone was only half the battle. How they shaped it reveals another layer of their genius. Instead of carving perfectly smooth, rectangular blocks, they often left the stones with deliberately irregular, bumpy faces. This might seem counterintuitive, but it created a powerful advantage. When two rough, uneven surfaces are pressed together under immense weight, they lock into one another. The microscopic peaks and valleys create friction and a mechanical interlock, preventing slippage far more effectively than two smooth planes ever could. It was a way of letting the stone's own natural texture become part of the binding agent. Furthermore, master stonemasons would orient each block according to its natural grain, placing it so that its inherent strength aligned with the direction of the load, much like how wood is strongest along its grain. This intimate knowledge of material, from the planetary scale of geology down to the crystalline structure of a single rock, transformed brute stone into a collaborative partner. Each irregular block was a unique piece in a three-dimensional puzzle, its shape and placement a calculated decision for collective stability. The silent testimony of these choices is all around us, in platforms that have not shifted an inch in 1,000 years. Yet this raises a compelling puzzle. These perfectly chosen, expertly shaped stones were still individual pieces. How did ancient builders transform a pile of magnificent rocks into a single, monolithic entity that could withstand earthquakes and the slow creep of time? The answer lies not in the stone itself, but in the invisible spaces between them. The spaces between the stones held the true secret to their permanence. Without a drop of mortar, ancient builders achieved a bond so perfect it defied the very forces that sought to pull them apart. This was the art of dry stone masonry, a silent conversation between gravity and geometry. Each block was not merely stacked, it was precisely keyed into its neighbors, creating a unified mass where the strength of the whole was far greater than the sum of its parts. The principle was deceptively simple, rely on weight and shape alone, but the execution was a masterpiece of patience and foresight. Stonemasons would spend days, even weeks, on a single block, slowly chiseling and grinding its faces until it fit its designated space with a seam so tight a blade could not slip between. They did not seek perfect rectangles. Instead, they shaped polygonal blocks, each with multiple angled faces. When placed together, these irregular shapes created a three-dimensional interlock. Under the immense downward pressure of the platform's own weight, these angled faces pushed against each other, translating vertical force into lateral stability. The entire wall or platform became a single, coherent entity, resisting shear forces from earthquakes or settling in a way that straight, stacked walls never could. The Cyclopean walls of Mycenaean, the massive supporting platforms for its legendary citadel, are a breathtaking example. These colossal limestone boulders, some weighing over 20 tons, were fitted together with astonishing precision. Their irregular, multifaceted shapes locked together like a giant's puzzle, creating a foundation so stable it has anchored the stories of Agamemnon for over 3,000 years. This method reached its zenith with the Inca stonemasons of the Andes. At sites like Sacsayhuaman or Ollantaytambo, the stonework is so precise it seems liquid, as if the rocks softened and flowed together before hardening once more. Archaeological studies reveal the genius behind this appearance. The Inca used a technique of trial and error fitting. A block would be roughly shaped in the quarry, transported to the site, and then meticulously dressed in place. Using harder stone hammers and abrasive sand, they would grind the contact surfaces, constantly testing the fit, shaving off minute slivers until the block settled into its place with a solid, resonant thud. The result was a jigsaw puzzle in stone, where every piece, with its unique contours, contributed to the structural integrity of the entire platform. Within this system, certain stones played specialized roles. Builders employed keystones, central blocks whose shape and position locked the surrounding pieces into place, much like the keystone of an arch. They also used tapered blocks wider at the top than the bottom. As the structure settled over centuries, these blocks would actually tighten their grip, sinking into a more secure position. This was construction that understood and planned for time itself, creating a platform that grew stronger with age. To stand before such a wall is to witness a profound kind of patience, a commitment measured in generations rather than years. It represents a physical dialogue between human intention and the immutable nature of stone. Yet this raises a final, fascinating question. For all its brilliance, dry stone masonry had its limits, especially in regions with less perfect stone or for builders with different cultural needs. When the perfect interlock was impossible, or when a different kind of monument was desired, what did they use to bind their visions together? The answer lies not in the stones, but in the earth they walked upon. But the perfect interlock was not always possible. In regions where stone was scarce or difficult to shape, or where the vision called for a smoother, more sculptural form, builders turned to a different kind of magic. They learned to create stone from scratch, using the very earth beneath their feet as a binding agent. This journey begins in the mixing pits, where simple mud and clay were transformed into the glue of civilization. At its most basic, a mortar of clay, water, and straw was a revolutionary tool. It filled the inevitable gaps between irregular stones, creating a more uniform surface for the next layer. More importantly, it acted as a cushion, distributing the immense weight of the platform more evenly across the stones below. This prevented stress from concentrating on a single high point, a flaw that could crack even the strongest granite over centuries. Yet, simple clay had a fatal weakness. Water could soften it, washing it away and leaving the structure vulnerable. The quest for a permanent binder was on. This led to one of humanity's greatest chemical discoveries, lime mortar. The process was alchemy. Builders would collect limestone or seashells, materials rich in calcium carbonate, and burn them in a kiln at intense heat. This drove off carbon dioxide, leaving behind a powdery, caustic substance called quicklime. When water was added to this powder, a violent reaction called slaking occurred, producing a paste known as slaked lime. Mixed with sand and water, this paste could be troweled between stones. Then, something remarkable happened. As it dried, it began to reabsorb carbon dioxide from the air, slowly turning back into solid calcium carbonate, essentially artificial limestone. The mortar did not just dry, it petrified, becoming as durable as the stones it joined. But the true breakthrough was yet to come. Some builders observed that adding certain materials to the lime mix created a mortar that could set even underwater or in perpetually damp conditions. This was hydraulic mortar, and its secret was pozzolana, a fine volcanic ash. When mixed with lime and water, the silica in the ash reacted chemically to form a crystalline structure that hardened in the presence of moisture, making it ideal for foundations, cisterns, and platforms in wet environments. The Romans perfected this into opus caementitium, their revolutionary concrete. They combined lime, pozzolana, and an aggregate of fist-sized rocks and rubble to create a material that could be poured into wooden forms. This allowed them to build the massive, monolithic cores of platforms and temples that were both strong and somewhat flexible, able to withstand minor ground movements without cracking. The enduring foundations of structures like the Temple of Saturn in the Roman Forum stand as testament to this engineered stone. Materials science reveals even more subtle refinements. Across cultures, builders experimented with additives to improve their mortars. In some regions, they mixed in animal hair or plant fibers to provide tensile strength, helping the binder resist shrinkage cracks as it cured. Others added egg whites, rice paste, or even animal blood, organic compounds that altered the setting time and final hardness. Each recipe was a localized solution, a dialogue between available resources and environmental challenges. The production of these binders was a communal ritual in itself. The kilns burned for days, tended by keepers of a dangerous flame. The slaking pits bubbled and steamed, requiring careful timing. The final mix was a guarded formula passed down through generations of masons. This chemical knowledge, often shrouded in the language of craft and tradition, was in fact a profound understanding of material transformation. It allowed builders to conquer the final frontier of instability, water itself. By creating a binder that could thrive in damp conditions, they could place their massive platforms in previously impossible locations, near rivers, in marshes, or in regions of heavy rainfall. The platform was no longer at the mercy of the environment. It was now in a fortified partnership with it. Yet, even the strongest mortar could not solve every problem of weight and movement. What happened when the ground itself decided to shift in a more dramatic way? Even the most ingenious mortar could not defeat the silent, relentless enemy of every stone structure. Water does not attack with force, it works through patience, seeping into microscopic cracks, freezing and expanding, dissolving binders, and softening the very earth that supports the weight. Ancient builders understood this threat on a visceral level, and their response was not to fight water but to guide it, to design platforms that invited moisture to leave. This was the art of hydrological engineering, woven into the fabric of the structure from its very conception. The first line of defense was the shape of the platform itself. Builders almost never constructed a perfectly flat upper surface. Instead, they engineered a subtle, almost imperceptible convexity or a gentle slope, often just a few degrees. This camber ensured that rainwater never pooled on the sacred stage above, but instead sheeted off the edges. To catch this runoff, they integrated gutters and channels directly into the stonework, often carved from single blocks, directing the water away from the foundation walls and into carefully planned drainage courses. But managing surface water was only half the battle. The greater challenge lay beneath, in the hidden realm of groundwater and capillary rise, where moisture could wick upward through the soil and into the platform's core. Here, their solutions were brilliantly layered. Within the foundation itself, they constructed what we might call a capillary break. A thick stratum of coarse gravel or sand was laid above the compacted subsoil. Because the pores between these large particles are too big for capillary action to work effectively, this layer acted as a barrier, stopping groundwater from being drawn up into the finer materials of the platform above. It was a simple, physical principle applied with profound foresight. More active systems were also employed. Archaeologists at sites like Great Zimbabwe have uncovered extensive, hidden networks of drainage channels built right into the massive granite platforms. These were not afterthoughts, but integral components constructed simultaneously with the walls. Channels lined with flat stones directed subsurface water away from the foundation, sometimes leading to deep soakaways or out to the surrounding landscape. They also incorporated weep holes, small, intentional gaps left in the lower courses of masonry. These allowed any water that did penetrate the structure to escape, preventing pressure from building up behind the walls, which could cause bulging or collapse. The entire platform was designed to breathe, to let water flow through it in a controlled manner, rather than trapping it inside. In some advanced systems, builders created what we now term French drains, trenches filled with loose stone that acted as subterranean rivers, collecting and redirecting groundwater long before it could reach the critical load-bearing layers. This holistic approach to water management reveals a sophisticated understanding of the platform as a living system interacting with its environment. It was not an inert monument but a dynamic participant in the hydrological cycle. By giving water a clear and dignified exit, they removed its destructive power. The stones remained dry, the binders intact, and the compacted earth below stayed firm. This silent, flowing infrastructure is a testament to a philosophy of working with natural forces, not against them. It asks us to look beyond the grand facades and see the intelligent, often invisible systems that granted these structures their legendary longevity. Yet, water is a predictable adversary flowing always downhill. A far more unpredictable test awaited these platforms, a sudden, violent conversation with the moving earth itself. A stable platform must also survive the earth's sudden, unpredictable movements. The ground does not always remain still, and ancient builders in seismic zones understood this reality intimately. Their fourth principle was not rigid defiance but intelligent adaptation, designing structures that could sway, absorb, and dissipate energy rather than shatter against it. This is the mastery of dynamic stability. They began by rethinking the very shape of their walls. Instead of building perfectly vertical surfaces, they constructed battered walls which slope gently inward as they rise. This simple taper dramatically lowers the structure's center of gravity, making it far less likely to topple when shaken. The weight is pulled toward the core, anchoring the entire platform. Inside these thick, sloping walls, they often incorporated hidden buttresses, ribs of stone that reinforced the structure from within, like a skeleton providing internal strength against lateral pushes. But the true genius was in the joints. While their masonry was famously tight, they sometimes introduced deliberate points of flexibility. At certain critical layers, builders would place a thin bed of fine sand or clay between the stone courses. During an earthquake, these granular layers allowed the stones above to slide minutely, absorbing and redistributing the seismic energy horizontally. The stones would settle back into place once the tremor passed, having moved as a unified mass rather than as individual blocks cracking under strain. Architectural analysis of sites in active zones reveals even subtler adaptations. Doorways and windows were often trapezoidal, wider at the bottom than the top. This shape, far from being merely stylistic, is incredibly seismically resilient. As a tremor shakes the building, the angled sides of the opening guide the lintel stone above to settle more securely into its seat, actually tightening the structure rather than weakening it. Similarly, long walls were often built with a slight outward convex curve. When lateral force pushed against them, this curve helped channel the energy along the wall's length, allowing it to flex and dissipate the shock. The Hittite capital of Hattusa, built in a region prone to tremors, stands as a textbook of these ancient seismic codes. Its monumental gateways and temple platforms employ precisely these battered profiles and trapezoidal forms. The builders did not have our scientific vocabulary, but they possessed a profound empirical understanding of how mass and geometry interact under stress. They were engineering for movement. This leads to a deeper insight about their relationship with time. They knew that even without earthquakes, all heavy structures settle slowly into the earth. So they planned for it by carefully calculating the platform's center of gravity and ensuring a broad, tapered base. They designed a settlement pattern that would be uniform and controlled. The platform would sink as a single entity, maintaining its integrity for centuries. This was stability redefined not as absolute stillness, but as managed, graceful movement. It acknowledges a fundamental truth: the earth breathes, and the greatest structures are those that learn to breathe with it. The true test of a platform is not the day it is finished, but the century that follows. Ancient engineers understood that stone and earth are not static. They are participants in a slow, inevitable dance with gravity. Their most profound insight was to plan for this movement, to design not for a moment of perfection, but for a future of graceful settling. This was the principle of planned settlement, a form of architectural foresight that considered time itself as a construction tool. Think of it as building a slight, intentional sag into the very center of a massive platform. An engineer standing at the dawn of construction would knowingly design the foundation to be a fraction higher around the edges. Why? Because they understood that the immense weight of the structure would compress the materials beneath it, most intensely at the center where the load was greatest. By preemptively building in this subtle camber, they ensured that after decades of slow compression, the platform would eventually settle into the perfectly level plane they intended. It was stability achieved through a planned journey, not an instant state. This required a deep geotechnical intuition. Builders selected and layered their foundation materials with settlement in mind. They might place more easily compacted soils or loosely packed rubble in the center, while using denser, more resistant materials like packed clay or gravel at the perimeter. These materials would compress at different, predictable rates under pressure, guiding the entire platform down uniformly. The goal was to prevent the nightmare of differential settlement, where one corner sinks faster than another, creating shear forces that crack even the strongest stonework. Expert analysis of ancient sites reveals markers, sometimes simple stones set at a consistent height, that builders used to monitor this slow descent during construction. They would check these benchmarks over seasons, adjusting their work to correct the settlement path, ensuring the platform descended as a single, unified mass. The most majestic embodiment of this principle is not a single building but an entire landscape. Consider the ancient tells of the Near East, those massive, layered mounds that mark the sites of cities like Jericho or Ur. These are not natural hills, they are the accumulated result of planned settlement on a civilizational scale. A community would build a platform and structures of mud brick. Over generations, these would weather, compress, and eventually be leveled to form the foundation for the next city layer. Each generation built upon the settled ruins of the last, knowingly adding to the mound's height and stability. The platform grew not through one grand plan, but through 1,000 acts of construction, each one accepting and utilizing the settlement of the era before. The tell is a monument to patience, a physical record of time where each layer represents a chapter of controlled descent and renewed ambition. This long-term thinking transforms our understanding of their achievement. They were not just stacking stones, they were orchestrating a slow-motion performance with the earth. They built with the confidence that time would finish their work, compacting their layers into an ever more solid whole. It represents a partnership with the future, a trust that the structure would reach its ideal form long after its original architects had passed. This leads us to a final, fascinating layer of their practice. If they could plan for the physical settling of earth and stone, did they also embed other, less tangible forms of reinforcement? Did they weave the very beliefs of the community into the fabric of the platform to ensure its endurance in ways that go beyond engineering? The stones were set, the drains were carved, yet for the builders the work remained incomplete. A platform needed more than physical strength, it required a soul, a reason to endure. This final layer of stabilization existed in the realm of belief, where engineering met ceremony to create a place that felt eternally anchored. Before the first cornerstone was laid, a sacred act often took place in the excavated earth. Foundation deposits, carefully chosen objects, were placed into the ground as a permanent covenant between the people and the place. These were not random trinkets. Archaeologists have uncovered caches of precious materials, inscribed tablets bearing the names of kings or prayers to deities, ceremonial tools, and sometimes even small-scale models of the very platform being built. Beneath the corners of Mesopotamian ziggurats, deposits might include beads of lapis lazuli, carved cylinder seals, or tablets asking the gods to grant the structure long life. The act was profound. It embedded the community's hopes, identity, and most valued possessions literally within the foundation. It transformed the platform from a construction site into a living archive of collective memory. The offering was a spiritual keystone, a plea and a promise that this place was sanctified, watched over, and therefore protected from the chaos of time. This ritual practice reveals a crucial insight. Stability was not just a physical property, it was a state of being granted by higher powers and maintained by correct relationship. The platform's permanence was guaranteed by metaphysical laws as much as by the laws of physics. To further lock the structure into this eternal order, builders aligned it with the cosmos itself. Cardinal orientation was not merely for grandeur, it was a source of strength. By aligning the platform's sides precisely with the four directions, they connected it to the fundamental axes of the universe. This created a sacred geometry, a microcosm of a stable, orderly cosmos. The platform became a fixed point in the celestial map, its endurance mirroring the predictable cycles of the sun, moon, and stars. Research suggests the dimensions themselves often followed sacred ratios, numbers believed to hold harmonic power, making the structure resonate with a perfection beyond mere measurement. This alignment served a dual purpose. It provided a celestial calendar for ceremonies, yes, but more deeply, it made the platform a participant in cosmic balance. If the heavens were eternal, then a structure in harmony with them could share in that eternity. The Great Platform at Mohenjo-Daro, for instance, shows a meticulous attention to cardinal alignment, its baked brick walls squaring precisely with the north-south axis. This was a statement written in geometry: we are part of something unchanging. So we see a complete philosophy of construction emerge. The physical techniques prevented collapse, but the rituals prevented oblivion. They addressed the human fear of being forgotten, of a legacy crumbling into dust. By weaving story, offering, and cosmic order into the very fabric of the platform, they created a structure that was culturally indispensable. Its loss would be unthinkable, not just as an engineering failure, but as a spiritual catastrophe. This ingrained the motivation for its care across generations. The platform was now a sacred trust, a living entity that demanded and received ongoing vigilance. How does a society maintain a promise made in stone over centuries? This final duty, the quiet work of preservation, becomes the ultimate testament to their success. The final stone was set, but the story of the platform was only beginning. Its endurance relied on a promise that stretched far beyond the lifetime of its builders, a cycle of watchfulness and care passed down like a sacred heirloom. Stability was understood not as a finished state, but as a perpetual conversation with time, a responsibility that demanded the hands of grandchildren and great-grandchildren. This was the unspoken chapter of their genius, the cultural tradition of cyclical repair and renewal. A generation of caretakers would arrive, their task not to build anew, but to listen to the whispers of the stones, to replace a single eroded capstone where water had begun its patient work, to clear the sacred drainage channels of centuries of silt. These acts, repeated over generations, were rituals of continuity. The knowledge required was immense, not just the craft of masonry, but the wisdom to diagnose subtle shifts, to understand which stone could be saved and which must be replaced to protect the whole. This social organization around maintenance was often woven directly into the fabric of religious and civic life. The care of the temple platform was a holy duty, a direct service to the gods and ancestors who dwelled there. Scheduled festivals might include not just ceremony, but a day of communal labor, where every citizen contributed to clearing debris or mixing a new batch of mortar according to the old recipes. This embedded the structure's physical health within its spiritual purpose, ensuring the knowledge of its upkeep never faded from communal memory. Common repairs followed a logic of preservation. Repointing mortar was a constant task, as even the strongest lime mix could eventually erode on the windward side. Caretakers would carefully chip out the old, friable material and press in new mortar, matching the original composition as closely as possible. Facing stones polished smooth by centuries of weather might be carefully turned to present a fresh, more resistant surface to the elements, or entirely new stones quarried and shaped to fit the ancient sockets. The most critical and often most hidden work was the maintenance of the hydrological systems. Teams would descend to clear the subterranean drainage channels, ensuring the platform's hidden veins remained open, protecting its heart from the slow poison of trapped moisture. This cycle of care created a fascinating archaeological record, where one civilization's act of preservation became the foundation for another's ambition. Across the ancient world, later builders often chose to build upon and stabilize the platforms of their predecessors. They recognized the inherent strength of the existing foundations, seeing them not as ruins but as a head start granted by history. They would add new layers of fill to correct settlement, rebuild collapsed sections in their own architectural style, and in doing so, extend the platform's life for another millennium. A powerful example is the enduring platform of the Acropolis in Athens. Its story is not one of a single construction, but of continual refurbishment across wildly different eras. The Mycenaeans first fortified the hill, Centuries later, the Athenians of the classical age built their sublime marble temples upon those ancient foundations. After damage in conflicts, Romans repaired and reinforced the structures. In later centuries, the platform served as a fortress, a palace, and each successive group, while adapting it for their own needs, took pains to maintain its core integrity. They became part of its unbroken chain of caretakers. This sustained care forces us to shift our perspective. The true marvel is not just the initial act of engineering, but the cultural engine that preserved it. It represents a long-term pact between a society and its symbols, a recognition that what is truly permanent must be actively cherished. To understand these techniques today requires a special kind of detective work, piecing together not just how they were built, but how they were loved into eternity. The quiet work of preservation leaves its own distinct signature in the stone. To understand the full story, we must learn to read these signatures without disturbing the sacred silence of the site. This is where the tools of the modern detective take over, translating whispers from the deep past into a language we can see. In a field tent or a quiet lab, archaeologists now peer directly into the heart of a platform without lifting a single stone. The key is a suite of non-invasive technologies that listen, scan, and map the hidden world below our feet. Ground-penetrating radar, or GPR, is like giving the Earth an ultrasound. A technician pushes a sled across the ground, sending pulsed radio waves into the soil. These waves bounce back whenever they hit a change in density, a buried wall, a void, or a different layer of fill. The returning signals paint a ghostly, cross-sectional image on a screen, revealing the platform's internal anatomy, its strata and hidden chambers, as clearly as if we had X-ray vision. Another powerful tool is electrical resistivity tomography. By inserting a series of metal probes into the ground and passing a small electrical current between them, scientists can measure how easily the soil conducts electricity. Dry stone offers high resistance, while damp clay or buried organic material conducts more readily. By taking thousands of measurements across a grid, they build a three-dimensional resistivity map, highlighting differences in material and moisture that outline ancient foundations, compacted pathways, and even long filled in construction trenches. From the air, the story gains even greater clarity. LiDAR, which stands for light detection and ranging, uses lasers fired from an aircraft or drone to measure the distance to the ground with incredible precision. By stripping away the forest canopy digitally, LiDAR reveals the subtle contours of the land, exposing ancient platforms, terraces, and roadways that have been swallowed by jungle for 1,000 years. It shows not just the structure, but its relationship to the entire landscape, how it fits into the natural drainage and topography. These datasets do not interpret themselves. They flow into powerful computers where specialists build intricate digital models. They can run simulations, testing how different construction sequences would have affected settlement patterns, or how seismic waves would travel through the unique layering of materials. A compelling case is unfolding beneath the Roman Forum, using a combination of GPR and core sampling, where a narrow, hollow drill extracts a cylinder of material for analysis. Researchers have mapped the deeply buried platforms of temples like that of Saturn. They can see the precise sequence of the Roman concrete foundation, the layers of gravel and sand, and even evidence of earlier Republican-era structures that were leveled to create a stable base. The core sample is a time capsule, a physical record of every layer of history compressed into a tube of earth and stone. Each band of color, each fragment of pottery or charcoal, tells a chapter of the construction and maintenance story. This forensic toolkit allows us to move from speculation to revelation. We are no longer just admiring the surface, we are conducting a respectful dialogue with the structure's soul. We can see the builder's corrections, the patches made by later generations, and the clever voids they left for drainage. It transforms the platform from a silent monument into a dynamic archive, its layers waiting to be read like the pages of a book written in soil and stone. This new vision raises a profound question. With these eyes that can see through time, what do we discover when we compare the solutions crafted by cultures separated by continents and oceans? Do their methods share a common language of stability? Isolated on their Mediterranean island, the builders of Malta faced a monumental puzzle with limited resources. Their solution, crafted over 1,000 years before the pyramids, was a masterclass in leveraging local geology with breathtaking ambition. The temples of Haga, Kim, and Mnajdra rise from massive stone platforms that seem to erupt directly from the rugged coastline. These foundations are not random piles of rock. They are deliberate engineering feats built upon the island's unique geological personality. The bedrock here is coralline limestone, a hard, dense material formed from ancient coral reefs. This became their unshakable table, but instead of trying to flatten this naturally uneven surface, the Neolithic builders worked with its contours. They carefully shaped the sloping bedrock into a series of broad, level terraces. Each terrace acted as a stable shelf, a stepped foundation that effectively broke the immense platform into manageable, gravity-resistant segments. This terracing distributed the colossal weight down the slope, preventing a single, unstable mass from wanting to slide toward the sea. Upon these prepared shelves, they began their work with stone. The most iconic feature is the use of truly megalithic blocks, some weighing over 20 tons. These were not finely dressed ashlars but roughly shaped giants, their sheer mass and friction providing primary stability. They were laid in horizontal courses, with each layer carefully set back slightly from the one below, creating those distinctive battered walls that lower the center of gravity. The question of how they moved these titans has long fascinated researchers. Current analysis strongly supports the use of stone spheres, carefully carved limestone balls found in abundance at the sites. These spheres likely acted as roller bearings. Teams would have levered a block onto a track of wooden timbers, placed the stone spheres beneath it, and then pulled with ropes, the spheres rotating to carry the immense weight forward in a controlled, low-friction glide. Levers made from massive tree trunks would have provided the precision for the final, inch-by-inch placement into their prepared sockets. Beneath the visible platform, archaeology reveals a hidden world of stabilization. Excavations show complex networks of trenches cut into the bedrock. These were not merely construction footings. They served as drainage systems to channel rainwater away from the foundation, and also as repositories for sacred deposits. Into these trenches, the builders placed ceremonial objects, animal remains, and tools, spiritually anchoring the temple to the land in a practice that married physical security with divine sanction. The Maltese builders also displayed a sophisticated understanding of their materials. While the hard coralline limestone formed the backbone, they selectively used a softer stone called Globigerina limestone for interior walls, altars, and decorative slabs. This stone was easier to carve with stone and antler tools, allowing for the elaborate spirals and patterns that adorn the temples. This strategic choice shows a nuanced approach, using the toughest material for structural integrity and the more workable stone for artistic and ceremonial expression. The story deepens at the Terraced Temples complex. Here we see not a single act of construction, but a saga of adaptive stabilization spanning centuries. The site shows clear, successive building phases where later temples were carefully constructed adjacent to, and even incorporating the walls of earlier ones. New platforms were built abutting the old, sometimes using the pre-existing structure as a retaining wall for new terraces. This practice demonstrates a living tradition of engineering knowledge, where each generation observed what worked, understood the settlement patterns of their ancestors' platforms, and built upon that legacy literally and figuratively. They were not just building temples, they were cultivating a sacred landscape of stone. Each new phase a dialogue with the stability of the past. From these island builders who mastered their limestone world, our journey takes a dramatic turn in geography and scale. We travel across an ocean to the Andes, where a different stone and a steeper challenge awaited. High in the thin air of the Andes, stone becomes something else entirely. Here, the Inca and their predecessors, the Tiwanaku, did not just build platforms, they performed a kind of alchemy, transforming granite and andesite into structures that feel less constructed and more grown. The seamless walls of Sacsayhuaman, the enigmatic platform of Pumapunku, these are not monuments to brute force, but to a profound, almost unimaginable precision. Their mastery lies in a trinity of principles: perfect dry stone fitting, complex polygonal geometry, and a hydrological intelligence that defies the harsh mountain climate. Modern engineers studying these sites are often left speechless, not by the size of the stones, but by the foresight in their placement. Every irregular angle, every subtle curve, was a calculated decision for seismic survival. In a land shaken by constant tremors, they built platforms designed to dance. The process began with a patient, thunderous conversation between stones. Using only harder stone hammers, masons would spend months on a single block. The technique was one of trial and refinement. A roughly shaped stone would be positioned next to its neighbor, and the masons would begin to dress the facing surfaces in place. They would pound, creating a dust of stone, and then test the fit. A high spot would be marked, ground down, and the test repeated. Over countless iterations, the two faces would gradually conform to one another until the block slid into its final position with a solid, airtight seal. The goal was not a smooth surface, but a perfect three-dimensional puzzle lock. The resulting polygonal walls, where each stone has multiple angled sides, are a masterpiece of distributed force. Under the immense weight of the platform, these angled joints push inward against each other, translating vertical load into lateral stability. During an earthquake, this interlocking mesh allows the entire wall to flex as a single, coherent unit. The stones can shift minutely along their complex boundaries, absorbing and dissipating the energy, then settle back into place once the tremor passes. It is architecture that embraces controlled movement as the secret to permanence. This geometry was supported by a sophisticated understanding of materials. Builders selected specific stone types for specific roles. For the foundational heart of a platform, they sought the densest, most durable andesite or granite. For intricate, decorative elements or areas requiring more precise carving, they might use a slightly softer volcanic stone. At the Coricancha, the Temple of the Sun in Cusco, this philosophy is crystallized in a breathtaking curve. The retaining wall of its sacred platform is a sweeping, serpentine line of perfectly fitted polygonal stones. This curved form is not merely aesthetic, it is structurally superior. The convex shape helps channel lateral forces along the wall's length, making it far more resistant to spreading or collapse than a straight wall would be. It is a ribbon of stone woven tightly against the earth. Yet, even this perfect stonework would be vulnerable without a way to manage water. The Andean climate delivers torrential rains and freezing temperatures. The builders' response was a hidden network of drainage that protected their platforms from within. They constructed deep foundations of loose gravel that acted as capillary breaks, and integrated subtle channels and weep holes into the masonry itself, ensuring that any water that penetrated would be guided harmlessly away before it could freeze and expand. The platform was engineered to breathe in the storm and remain dry at its core. To stand before the polished, interlocking stones of an Inca platform is to witness a dialogue between human patience and geological time. They understood that true stability was not a static condition, but a dynamic, intelligent relationship with the forces of the world. From this mountainous realm of seismic wisdom, our journey descends toward the sea, to an island civilization that faced a completely different, yet equally formidable, set of elemental challenges. The stonework of Mycenae speaks in a different language, one of raw power and colossal scale. Here, the foundational platforms are built from giants. Limestone boulders, some weighing over 20 tons, are fitted together with a kind of brutalist precision, a style so immense that later Greeks believed only the mythical Cyclopes could have moved them. This Cyclopean style is a masterclass in stability through mass and friction. The builders selected minimally shaped boulders, their natural, irregular contours becoming an asset. When two such massive, rough-faced stones are placed together, their jagged surfaces bite into one another, creating a powerful mechanical lock that resists sliding far more effectively than smooth, dressed stones could. The spaces between these megaliths were not left empty. They were strategically packed with a matrix of smaller stones and clay, a technique known as implecton. This rubble infill acted as a shock absorber, distributing weight and preventing the giant blocks from shifting independently. It transformed a collection of massive stones into a single, monolithic mass, a mountain of masonry. The genius extended to the points of greatest stress, the openings. Above the massive lintel stones of gateways and tomb entrances, Mycenaean engineers carved a brilliant architectural solution, the relieving triangle. This was a hollow, triangular space left in the masonry above the lintel. Its purpose was pure structural intelligence. The immense weight of the wall and platform above the doorway was directed away from the center of the lintel, channeled along the angled sides of the triangle, and down into the solid masonry on either side. This prevented the lintel, the weakest point in the wall, from cracking under the colossal load. The famous Lion Gate at Mycenae stands as the ultimate testament to this. Its monolithic lintel shielded by a massive triangular relief sculpture that serves this exact engineering purpose, beautifully disguising necessity as art. Placement was everything. These Cyclopean platforms were not built on flat ground, but on the very bones of the landscape. The citadel of Mycenae itself is perched atop a steep, rocky outcrop. The builders integrated their monumental walls and platforms directly into this natural fortress, using the existing bedrock as both a foundation and a part of the structure. They carved level beds into the living rock to seat their first course of boulders, creating that essential, unbreakable bond between the man-made and the natural. This strategic siting provided a formidable defensive advantage, yes, but also a profound geotechnical one. Building on the outcrop eliminated concerns about unstable subsoil, ensuring the platform rested on the most unshakable foundation imaginable. The approach to the so-called treasury of Atreus, a monumental Tholos tomb, showcases this philosophy on a processional scale. Its dromos, the long, walled entrance passage, is itself a feat of platform engineering. The walls lining this sunken corridor are built in the classic Cyclopean style, creating a stable, sloping avenue that leads the visitor downward, psychologically and physically, into the heart of the eternal resting place. The entire structure demonstrates how platform technology was used to frame experience and create a sense of awe, proving that stability could be the foundation for profound ceremony. From the sun-baked limestone of the Aegean, our search for ancient stability now turns toward a radically different environment, where the challenge was not building upon rock, but creating permanence from the very dust of the desert. The baked brick mountain of rises from the flat Mesopotamian plain, a man-made peak reaching for the gods. This is the Ziggurat, a form that redefined the very concept of a platform, not as a base for a temple, but as the temple itself. Its stability was an act of defiance against a landscape with no bedrock, no stone, and a climate of scorching sun and sudden, violent rains. The solution was a masterpiece of layered engineering, a terraced core built from the earth beneath their feet. At its heart was a simple, brilliant principle: compaction. builders would create a mound of locally excavated soil, rubble, and broken pottery, then layer it with millions of hand-made mud bricks. But this was not a careless pile. Teams of workers, likely moving in rhythmic processions, would tirelessly tamp each new layer, using heavy wooden pounders to compress the material, driving out air pockets and creating a dense, homogeneous mass. This compacted core became an artificial bedrock, a stable hill they sculpted into a sacred mountain. To protect this vulnerable earthen heart from the elements, they crafted an ingenious skin. The outer faces of each terrace were clad in a thick armor of fired bricks. These bricks, baked in kilns until they were nearly as hard as stone, were resistant to water and wind erosion. They were set in place with a mortar that was itself a technological marvel, bitumen. Ancient texts from the region provide precise recipes for this naturally occurring tar, which was heated and mixed with sand and fine aggregate. When applied, this bitumen mortar created a flexible, completely waterproof seal, a black, gleaming coat that shed rainwater like a duck's back, protecting the soft core within. The terraced form was itself a structural calculation. Each ascending level was deliberately set back from the one below, creating a series of receding shelves. This design dramatically reduced the load on the lower retaining walls. Instead of a single, massive vertical face holding back an immense weight of earth, the load was broken into a staircase. The weight of the upper terraces was borne largely by the compacted core directly beneath them, with only a portion transferred outward to the lower walls. This inward-sloping profile, called a batter, further lowered the center of gravity, making the entire structure incredibly resistant to toppling, even on its entirely artificial foundation. Within this colossal brick mountain, builders integrated hidden systems of reinforcement. The core was not a solid block of fill. Archaeological studies suggest the inclusion of internal buttresses, walls of brick running through the heart of the mound like a skeleton. These acted to bind the compacted material, preventing internal slippage or bulging. Perhaps even more clever were ventilation shafts, narrow, vertical channels left open during construction. These shafts allowed air to circulate deep within the core, helping to keep the earthen fill dry by evaporating any moisture that might penetrate from above or below, preventing the slow, destructive creep of dampness. A stunning example of this hydrological intelligence is found at the Ziggurat of Chogh Azanbil in Iran. Here, the builders faced the challenge of directing torrential runoff away from their sacred mountain. Their solution was a comprehensive, integrated drainage network. They constructed deep, subterranean channels lined with baked brick that ran from the highest terrace down through the core and out far beyond the base. These were not add-ons but built simultaneously with the ziggurat itself, woven into its fabric. At the ground level, a vast paved courtyard surrounding the structure sloped gently away, ensuring rainwater sheeted off quickly and was caught by a perimeter moat, a final barrier to protect the foundation from saturation. The ziggurat represents a philosophy of engineered permanence from impermanent materials. It transformed humble mud through fire and human effort into a form that aspired to the eternal. From these monumental, terraced mountains of the plains, the story of stabilization turns to a different kind of earth, one shaped not into peaks, but into vast geometric plains that held entire cities aloft. Across the Mississippi floodplain, the earth itself was reshaped into sacred geometry. The Mississippian mound builders faced a unique challenge, crafting permanent, monumental platforms not from quarried stone, but from the very soil beneath their feet. Their material was the soft, yielding earth of the river valley, and their genius lay in transforming this apparent weakness into a source of enduring strength. The result was a landscape of pyramids, but pyramids of packed soil, like Monk's Mound at Cahokia, a colossal earthen platform that remains the largest prehistoric earthwork in the Americas. Its stability over centuries is no accident. It is the product of a sophisticated, layered understanding of geotechnical engineering. The process began with an intimate knowledge of local soils. Builders did not simply dig and pile. They selectively harvested different materials for specific structural roles. They sought out dense, plastic clays from deeper strata for their binding properties and impermeability. They collected layers of wind-blown silt known as loess, prized for its cohesion and ability to compact into a firm mass. Even sand had its place, used in drainage layers or as a stabilizing mix. Each basket load of earth was a deliberate choice. Geoarchaeologists studying the mounds through soil cores and electrical resistivity have mapped this intentional layering. They find sequences of thin, distinct strata, like the pages of a book, each representing a single episode of construction. A layer of clay might be followed by a layer of loess, then a thin scattering of gravel. This alternating sandwich technique was crucial. It prevented the formation of continuous planes of weakness that could allow water to penetrate or cause the mound to slump as a single, unstable mass. Compaction was the ritual that gave these layers their power. After depositing a new lift of soil, perhaps only a few inches thick, work teams would engage in a communal act of consolidation. They used tamping tools, likely heavy wooden poles or stone mauls, to pound the surface in a systematic pattern. This relentless tamping drove out air, increased density, and mechanically interlocked the soil particles. The goal was to achieve a homogeneity that resisted internal shifting. To further reinforce this compacted mass, builders sometimes laid down sheets of woven grass or cane matting between the strata. This organic fabric acted as a tensile element, much like modern geotextile, holding the layers together and distributing loads more evenly, while also helping to control erosion during the construction phase itself. The slopes of these earthen platforms presented a constant threat, the risk of surface erosion from rain and wind. The builder's solution was a protective skin, a carefully engineered cap. They would finish a construction phase by blanketing the entire mound surface with a thick, impermeable layer of pure clay. This clay cap, often hardened by the sun, served as a waterproof barrier. It caused rainwater to sheet off the sides rather than infiltrate the core, where it could soften the compacted soils and trigger instability. Maintaining these slopes required additional support. Around the base of larger mounds and along steep terraces, archaeologists find evidence of retaining structures. These were often palisades of vertical logs sunk into trenches or revetments of stacked stone. These walls contained the earthen core, preventing the outward creep of soil under its own weight, and defining the platform's crisp, geometric form for generations. This was not a project completed in a single lifetime, but a legacy of care that unfolded over centuries. The mounds display clear, long-term settlement patterns. As the immense weight of the earth slowly compressed the underlying ground, the entire platform would subside uniformly. Rather than seeing this as failure, the community planned for it. In a cycle of renewal, they would periodically resurface their sacred platforms. They would add new, thin layers of carefully selected and compacted soil over the entire structure, restoring its height and profile and repairing any erosion on the clay cap. Each layer was a new chapter of commitment, a physical reaffirmation of the platform's importance. The Grand Plaza at Cahokia embodies this philosophy on a civic scale. This vast 50-acre expanse was not a natural flatland, but an intentionally engineered platform, meticulously leveled and filled to create a stable stage for the city's great gatherings. Its construction required moving astonishing volumes of earth to fill in low areas and create a uniformly elevated plain. This engineered ground provided drainage during rains, ensuring the plaza remained firm and usable, and it established a literal common ground, a stable foundation for the community's shared life. From these silent, grassy pyramids of the Mississippi, our journey through the ancient art of stabilization turns toward a civilization that married earth and stone on a legendary scale to the sun-baked banks of the Nile. The Nile's gift of life was also its greatest challenge. Each year, the river would swell, spreading rich, black silt across the valley, but also saturating the ground to a depth that could swallow a stone. To build a temple for eternity here on this soft, alluvial plain required a foundation that could outwit the water itself. The solution was not to build on the earth, but to build through it, creating an artificial island of stability in the ever-damp soil. Before the first colossal column drum was shaped, workers would dig deep, wide trenches far below the intended ground level. Into these voids they poured not concrete, but millions of basket loads of pure, clean desert sand. This was a stroke of hydrological genius. Sand is free draining, it cannot hold capillary water. By creating a thick, continuous bed of it beneath the entire temple platform, the builders effectively lowered the water table for their structure. Moisture from the annual inundation or the high groundwater would sink down, but could not wick back up into the foundation stones. The sand layer acted as a permanent, dry moat, isolating the sacred architecture from the dampness of the fertile plain. Sometimes, for added mass and drainage, they mixed this sand with graded rubble, broken stone, and pottery shards, compacting it into a rigid, well-drained raft. At Karnak, the processional way leading to the sacred lake is a masterclass in this approach. This grand avenue, meant for the statues of the gods to travel, was built upon a raised, linear platform. Excavations reveal its foundations are a deep matrix of sand and gravel, ensuring that even during the height of the flood, the path of the gods remained firm and unyielding, a dry causeway through the seasonal lake. The act of beginning such a project was itself a sacred covenant. Egyptology provides a poignant glimpse into the ritual that preceded construction. Before the foundation trenches were filled, priests would carefully deposit small, inscribed plaques, often of faience or precious metal, into the earth at the temple's corners. These foundation deposits bore the name of the pharaoh and prayers to the gods, asking for the structure's permanence. They were spiritual cornerstones, embedding the king's divine mandate and the temple's purpose into the very ground, blending metaphysical stability with the physical. Upon this prepared, drained base rose the platform itself, built from some of the most durable stone on earth. For the massive foundational courses, they used enormous blocks of sandstone or granite, quarried with relentless patience. The joints between these giants were not left to chance. Stonemasons employed a hidden reinforcement, metal dovetail clamps. These were U-shaped or butterfly-shaped clamps, usually of copper or bronze, set into matching slots carved into the tops of adjacent stones. Once in place, molten lead was often poured around them, locking the clamp into its socket. This created a hidden tensile link, binding the blocks together laterally, resisting any tendency to shift or separate under the immense cumulative weight. The platform was engineered as a single, interlocked machine. Even the surface of this great stone stage was meticulously calculated. While appearing perfectly flat to the eye, the paving stones of the temple platform were often laid with a subtle, convex curvature. This almost imperceptible camber meant that rare desert rains or water used in purification rituals would never pool and stagnate on the sacred ground. Instead, it would sheet gently toward the edges, where discreet channels carved into the stone would guide it away, protecting the platform from erosion and the insidious damage of standing water. The elevated forecourt of the Luxor Temple illustrates this holistic vision. Its majestic colonnades stand upon a raised platform that seems to grow from the earth. Modern archaeological probes around its edges have revealed the extensive, hidden foundation works that make this possible. A deep lattice of compacted sand and rubble that spreads far wider than the visible walls, like the roots of a great stone tree, ensuring stability for millennia. It is a monument built in two layers, the visible grandeur above, and the invisible, intelligent foundation below, each equally vital to its endurance. Having journeyed from Malta's limestone to the Andes granite, from Mesopotamia's brick mountains to the Mississippi's earthen pyramids, and now to the Nile's sand-drained foundations, a pattern emerges across the centuries. These builders, separated by continents and never knowing each other's names, were speaking a common language of stability. They all began by listening to the earth, choosing or creating firm ground. They mastered their local materials, transforming stone, brick, and soil into engineered partners. They designed for water, giving it a path of escape. They planned for movement, whether from settling earth or trembling ground, and they infused their work with meaning, making preservation a sacred duty. This was not a collection of random tricks, but a universal engineering philosophy, a deep understanding that to build for eternity, you must first make peace with the forces of time. These scattered echoes from across the world begin to form a single, resonant voice. From the Andes to the Mississippi, from the Nile to the island of Malta, builders who never met, who worshipped different gods and spoke unrelated languages, arrived at the same profound conclusions about how to make stone and earth endure. This is not a coincidence, it is a testament to a universal human ingenuity, a shared set of principles that emerged wherever people dared to build for the ages. Comparative analysis by historians and engineers reveals a stunning convergence, a short list of solutions that every successful culture, in its own way, discovered and mastered. The first principle was always a dialogue with the earth itself. Whether it was the Mycenaeans building on a limestone outcrop, the mound builders selecting specific clays, or the Egyptians digging down to a bed of sand, they all began by seeking or creating a stable conversation with the ground. They understood that the foundation was not an afterthought, it was the first and most important chapter of the story. The second universal insight was the power of the layer. Stability was never achieved through a single, monolithic act, but through patient, stratified construction. The compacted cores of Mesopotamian ziggurats, the alternating strata of gravel and clay beneath Roman temples, the basket-by-basket lifts of the Mississippian mounds, all speak to this same truth, that permanence is built in increments, with each layer serving a distinct purpose in a collective defense against time and pressure. Then came the geometry of connection, the polygonal puzzle of Inca walls, the rough interlock of Cyclopean masonry, the hidden dovetail cramps in Egyptian platforms, all served the same function, to transform many pieces into one. They discovered that true strength lies not in the individual block, but in the intelligent relationship between blocks, creating a unified mass that could withstand forces no single stone could bear alone. And finally, every culture became a master of water. They did not see it as an enemy to be defeated, but as a force to be guided. The drainage channels of Great Zimbabwe, the capillary breaks in Andean foundations, the bitumen sealants of and the convex surfaces of Egyptian courtyards, all were different verses of the same hymn, a recognition that to endure, a structure must remain dry. This shared checklist, site, layer, bond, and drainage appears again and again like a silent code. What drove this independent convergence? The evidence points not to a lost super-civilization, but to a powerful, common driver, environmental adaptation. Faced with the specific challenges of their homeland, earthquakes in the Andes, annual floods in Egypt, soft soils in Mesopotamia, and torrential rains in Mesoamerica, human creativity was funneled toward similar, elegant solutions. The problem of permanence, it seems, has a limited set of correct answers, and our ancestors, through observation, trial, and deep patience, found them all. This shared heritage is a humbling reminder of a profound connection. It suggests that beneath our vast cultural differences, there exists a common language of problem solving, a universal engineering intuition that emerges when we ask the most ambitious questions of our world. The stones of Sacsayhuaman do not just speak of the Inca, they speak for humanity's enduring desire to create, to anchor our stories in the landscape, and to whisper across the centuries. This ancient collective wisdom, refined over millennia, now waits silently in the ruins and the standing stones. It prompts a compelling modern question. In our age of steel and concrete, what have we learned from this timeless dialogue with gravity? The silent wisdom of those ancient platforms is finding its voice once more, not in new ruins, but in the blueprints of a sustainable future. Modern architects and engineers, confronted with the ecological and social costs of disposable construction, are looking back to these millennia-old principles, not for nostalgia, but for revolutionary guidance. This is not a rejection of technology, but a profound integration where advanced materials science meets the timeless logic of passive stability. The core lesson is a shift in philosophy, from building structures that resist their environment for a few decades to designing systems that collaborate with natural forces for centuries. It begins with a return to the most fundamental of all ancient insights, the intelligent use of local materials. Green architects champion rammed earth construction, a technique echoing the compacted cores of Mississippian mounds. By compressing locally sourced soil within forms, they create walls with exceptional thermal mass, regulating temperature naturally and boasting a carbon footprint a fraction of that of concrete or steel. Similarly, the revival of dry stone retaining walls, built without mortar in the tradition of the Andes or Mycenaean, offers a permeable, beautiful, and eternally repairable solution for landscaping and erosion control, allowing water to pass through and eliminating the need for synthetic barriers. These methods ask a pivotal question: why transport materials across the globe when the solution is literally beneath our feet? This ancient logic extends to water management, a field where modern engineering is relearning humility. Instead of relying solely on complex, energy-intensive piping and pumps, landscape designers now create bios walls and permeable paving, inspired by the capillary breaks and graded drainage of ancient platforms. These systems allow rainwater to infiltrate the ground on site, recharging aquifers and preventing the destructive runoff that overwhelms concrete cities, mimicking the hydrological intelligence that kept temple foundations dry for thousands of years. Perhaps the most critical relearning is in how we design for movement. Contemporary seismic codes in earthquake-prone regions are increasingly informed by forensic studies of ancient failure and success. Engineers analyze why certain Inca walls stood while modern buildings nearby collapsed, leading to innovations in base isolation and damping systems that conceptually mirror those ancient principles of flexibility and energy dissipation. We are learning to build structures that can sway, not break, understanding that dynamic stability is the true secret to longevity in an active world. The economic and ecological argument for this long-term view is compelling. Building for durability using local, low-embodied energy materials drastically reduces maintenance costs and environmental impact over a structure's life cycle. A rammed earth building or a dry stone wall requires minimal energy to create and can last for generations with simple, traditional repairs, challenging the modern paradigm of planned obsolescence. This philosophy is vividly demonstrated in the restoration of historical sites themselves. At places like the Alhambra in Spain or temples in Cambodia, conservators are increasingly turning away from modern cement, which can trap moisture and cause further damage. Instead, they painstakingly recreate the original mortars, using local lime, sand, and traditional additives, allowing the historic fabric to breathe and heal as it was designed to do. These restoration projects become living laboratories where the original builder's techniques are decoded and validated through practical application, proving their efficacy once more. This bridge between ancient and modern is more than a technical exchange. It is a cultural recalibration. It values resilience over speed, stewardship over extraction, and legacy over immediacy. The platforms that have watched millennia pass were not just feats of engineering, they were promises kept across generations. As we face our own era of environmental and social transition, their greatest lesson may be about time itself. They compel us to consider what we are building now that will still be teaching lessons 1,000 years from today, and what forgotten secrets of permanence still lie waiting in the quiet patience of stone and earth. Yet for all we have learned, the past holds its secrets close. Certain questions echo across the centuries, refusing to be settled by a single theory. These are not failures of understanding, but the healthy, beating heart of discovery, the puzzles that ensure the story is never truly finished. Consider the colossal sarsen stones of Stonehenge. We know they were dragged from the Marlborough Downs over 20 miles away, but the precise mechanics of that journey remain a subject of lively, sometimes heated, debate. Was it a continuous, grueling pull over rollers, a feat of pure manpower, or did the builders employ a more ingenious system, perhaps lashing the stones to wooden frames and leveraging the landscape's natural slopes, turning the journey into a controlled glacial slide? Each experimental archaeology project offers new data, yet a shadow of the original method still eludes us. Similarly, the breathtaking stonework at Pumapunku in Bolivia presents a mystery of precision that borders on the surreal. The andesite blocks there are cut with geometric exactitude, featuring notches, channels, and rebates that interlock with machine-like accuracy. How were these surfaces achieved with stone tools? Some researchers point to the possible use of specialized stone saws with abrasive sand, a process requiring unimaginable patience. Others suggest the knowledge of a harder, now lost material for cutting, or perhaps a sophisticated thermal technique involving heating and rapid cooling to spoil the stone before fine dressing. The debate is not about alien intervention, but about the upper limits of a refined, traditional craft that we have yet to fully replicate. These open questions extend to the very materials that bind the past together. The exact recipes for some Roman concretes, particularly those that set underwater in harbors, have been partially decoded but not perfectly duplicated. The specific blend of volcanic ash, the particle size, the mixing sequence, and the curing conditions created a chemical reaction modern science is still working to fully emulate. It is a humbling reminder that ancient artisans operated with a granular, tactile knowledge that our digital models are still catching up to. On a more tangible level, consider the curious case of the mysterious holes. At several ancient sites, from the bedrock around Stonehenge to foundations in the Mediterranean, archaeologists have uncovered carefully carved, cylindrical holes in the living rock. Their purpose sparks continual discussion. Were they simple post holes for temporary scaffolding or construction cranes? Could they have held liquids for some now forgotten leveling technique? Or might they be part of a complex anchoring system, holding wooden braces that stabilized walls during construction or seismic events? Each interpretation paints a different picture of the builder's moment-to-moment challenges. These ongoing debates are not a sign of confusion, but of a field vibrantly alive. They represent different schools of thought interpreting the same silent evidence. One school may emphasize the role of massive, coordinated labor, seeing the platforms as triumphs of social organization. Another might focus on the subtle application of forgotten technologies, small clever tricks that multiplied human effort. Both are likely pieces of the same truth. Embracing these mysteries does not diminish the achievement, it honors its complexity. It means accepting that the builder's full ingenuity may always hover just beyond our complete grasp, and that is precisely what draws us back, generation after generation. The platforms themselves are not closed books but open invitations, asking us to keep looking, to keep testing, and to remain humble before the quiet genius locked in stone. A platform built for eternity must face the slowest and most relentless opponent of all, a changing world. We often see these structures as monuments frozen in time, but they have lived through centuries of climatic drama, their stones bearing silent witness to droughts, deluges, and shifting seasons. Their survival or collapse is a direct report card on the builder's foresight, a test of how well their techniques could endure environmental forces that unfold over lifetimes, not construction seasons. Paleoclimatology, the science of ancient climates, provides the crucial context. By studying ice cores, lake sediments, and tree rings, scientists can reconstruct the weather patterns a platform endured. This data reveals haunting correlations. Periods of sudden abandonment often align not with invasion or social collapse, but with profound environmental stress on the very foundations of society. A prolonged mega-drought, for instance, could devastate the agriculture supporting a city, but its impact on the platform was more subtle and equally deadly. As the water table plummeted, the soils supporting the foundation could dry out and shrink, causing differential settlement that cracked walls from below. Conversely, a centuries-long shift toward wetter conditions presented a different threat. Drainage systems, perfectly adequate for the climate they were built in, could become chronically overwhelmed. Water would back up, saturating the compacted earthen cores that were never meant to be perpetually wet, turning stable fill into soft, unstable mud and triggering slow-motion slides. The chemical conversation between a structure and its atmosphere also evolved. Consider the lime mortars that bound so many ancient walls. Their strength relied on a specific chemical process, recarbonation, where the mortar absorbs carbon dioxide from the air to harden. In a stable environment, this creates a durable stone-like bond. But what if the climate changed? A shift to more acidic rainfall, perhaps from increased volcanic activity or environmental changes, would have slowly but perpetually attacked that mortar. The acidic water would dissolve the calcium carbonate, turning solid binder back into a weak, crumbly paste over generations. The platform would not fall in a day. It would simply lose its grip stone by stone as the glue of civilization washed quietly away. This fate highlights the difference between building for the present climate and building for climate variability. The most resilient platforms were those designed with a margin of safety, with overbuilt drainage and mortars mixed with additives like pozzolana that resisted a wider range of conditions. Compare the fates of platforms in radically different environments. In arid regions like the Egyptian desert, the primary enemy was not water, but the absence of it, followed by rare but violent flash floods. Platforms here, built with deep sand foundations and efficient runoff channels, often fared spectacularly well for millennia, preserved by the very dryness that defined them. Their stability was a product of environmental consistency. In humid, temperate climates, however, the assault was constant. The freeze-thaw cycle is a brutal mechanical force. Water seeps into microscopic cracks in the stone or mortar during autumn rains. When winter comes, that water freezes and expands by nearly 10%, prying the crack open a tiny bit wider. With each annual cycle, the crack grows, spalling flakes of stone, widening joints, and slowly, inexorably, reducing solid masonry to rubble. Platforms in these zones that survived demonstrate ingenious adaptations, like the use of extremely dense, non-porous stones for the outer courses, or mortars with flexible organic binders that could accommodate slight expansion without cracking. Perhaps the most poignant lesson comes from the coastlines. A platform built 1,000 years ago on what was stable, dry land may now be partially submerged or crumbling into the sea. This is not merely erosion, it is often evidence of subsidence coupled with rising sea levels. The very weight of the massive stone structure can slowly compress the soft soils of a coastal plain, causing it to sink gradually over centuries. When combined with the global sea level rise that followed the last ice age, the effect is a losing battle with the ocean. The foundations, perfectly sound in their original context, are eventually undermined by saltwater, wave action, and a water table that rises to meet them from below. Seeing a ceremonial platform being lapped by tides is a powerful reminder that environmental change is not a modern invention. It is a permanent feature of planetary history. The builders' foresight had limits bounded by the climatic knowledge of their age. Their legacy, therefore, is twofold. It is in the stones that still stand, testifying to their deep understanding of material and force, and it is equally in the stones that have fallen, offering sobering lessons in the humility required to build on a planet that is never truly still. The stones that remain pose a profound and delicate question to the present. Do we catch them as they fall, or do we allow gravity to have its final say? This is the quiet, urgent debate at the heart of modern heritage conservation, a field where every decision is a negotiation between the past and the future. For the massive platforms we have explored, the dilemma is especially acute. Their stability was engineered for the ages, but time, tourism, and environmental change now apply pressures their original builders could not foresee. The core conflict is stark: intervene with modern techniques to ensure safety and longevity, or practice minimal intervention, preserving the authenticity of decay as a historical document in its own right. There is no simple answer, only a spectrum of philosophies, each with its own compelling logic. On one end stands the principle of anastylosis, the careful reassembly of a monument using its original, fallen pieces. This approach, famously applied at the Acropolis in Athens, seeks to give the public a tangible understanding of the structure's original form and scale. It is a powerful act of resurrection, but it requires absolute certainty about where each stone belongs, and it inevitably introduces new, unseen supports. More common is the philosophy of consolidation, where conservators work like archaeological surgeons, aiming to stabilize without altering. Their toolkit is precise. They might use fine needles to inject specially formulated lime grout into hidden voids within a wall, filling the empty spaces that threaten collapse without obscuring the original masonry. For platforms showing signs of imminent failure, temporary structural shoring with adjustable steel frames can be installed, not as a permanent solution, but as a life support system that buys time for study and careful planning. When replacement is unavoidable, the goal is compatibility. Conservators will often quarry stone from the original source, if it still exists, and hand-dress it to match the ancient profile, ensuring the new piece bears the weight and weathers in harmony with the old. Yet the most cautious school of thought argues for restraint. These conservators see value in the ruin itself, in the narrative of its decay. They advocate for non-intrusive measures, like improving drainage around a platform's base to remove the source of the problem, rather than treating the symptoms in the stone. They warn of well-intentioned but irreversible mistakes, where modern, non-breathable cement is used to repoint ancient joints, trapping moisture inside and accelerating the very decay it was meant to stop, or where a clumsy reinforcement alters the structure's load paths, creating new points of stress. The ongoing work at the platform of the Eagles at Chichen Itza embodies this complex balancing act. Here, conservators face a monument suffering from centuries of erosion and the wear of countless footsteps. Their process is painstakingly slow. They meticulously document each stone, map every crack, and analyze the composition of the original mortar. Before any physical work begins, they debate the ethics of each potential action. Should a leaning wall be straightened, or simply prevented from leaning further? Can a missing decorative element be recreated based on fragments, or should its absence be accepted as part of the platform's story? The work that follows is a dialogue with the original builders, using modern science to extend the life of their ancient engineering while striving to leave no visible trace of the modern hand. This ethical conversation forces us to reflect on the purpose of preservation itself. Are we saving these platforms for our own understanding, or are we stewards holding them in trust for generations we will never meet? The choice between intervention and conservation is ultimately a question about the kind of legacy we wish to receive and the kind we are willing to pass on. It asks us to consider whether the greatest honor we can pay to these testaments of human ingenuity is to freeze them in time, or to respectfully accompany them on their long, slow journey back to the earth. The story of these platforms is a journey from the earth to the heavens. It begins with a careful hand testing the soil and ends with a community's deepest hopes sealed in stone. This was never a simple act of stacking rocks. It was a holistic philosophy of endurance, a seamless blend of keen observation, practical science, and profound belief. Our ancestors were master engineers in the truest sense, reading the language of the landscape and translating it into monuments that could hold a conversation with time itself. They teach us that stability is not a single technique, but a symphony of solutions, each one addressing a different voice in the chorus of natural forces, gravity, water, and the slow, shifting earth. Their legacy is a testament to human resilience and foresight, a reminder that the most enduring creations arise from a partnership with the world, not a domination of it. A modern structural engineer, after studying the seismic genius of Inca walls, once remarked that the experience was deeply humbling. It forces you to reconsider what true innovation means, and to recognize that some of the most elegant answers to our greatest challenges were discovered not in laboratories, but in quiet dialogue with stone and sky. This exploration invites you to look with new eyes at the old stonework in your own community, at the retaining walls, the church foundations, or the aged steps in a city park. Look for the signs of that ancient conversation, and we would love to hear from you which ancient site with its silent, steadfast platforms fascinates you the most. Share your thoughts in the comments below. If you enjoyed this deep dive into the mysteries of our shared past, please subscribe. There are countless more stories waiting in the stone, and we are just beginning to listen.